Computer. Welcome to Doc Waller's Earth and Space Report for Friday, September 24th, 2021. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a rainy evening in Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. Today, we are joined by members of the Rockport Research Explorers, Rockport Cultural Council, Gloucester Area Astronomy Club, colleagues, friends and family, and other curious folk. Thank you for coming. This evening, I'm delighted to be hosting Dr. Mark Reid, a senior astronomer at the Harvard-Smithsonian Center for Astrophysics in Cambridge. Mark earned his PhD in planetary science and astronomy from Caltech. He has since carried out pioneering research in radio astronomy, mostly while at the Center for Astrophysics. A member of the National Academy of Sciences, Mark has received the Tinsley Prize of the American Astronomical Society, the Millman Award of the Astronomical Society of the Pacific, and the Jansky Prize of the National Radio Astronomy Observatory. This evening, he will share his research on mapping the Milky Way. Having known Mark at the Center for Astrophysics and more recently here in Rockport, where he has a home, I'm thrilled to have him here tonight. So without further ado, please welcome Mark to our gathering.
Okay, I'll share my screen.
Sure thing.
Okay, let's go. So I've been involved in a pretty big project that's trying to make a plan view map of the Milky Way. I've been doing this for about 15 years. I've got about 5 more years to go if I make it that long. But it's been great fun. So let me just start here. I think most of you are familiar with the Milky Way from how it appears. This is a great picture taken by Wally Pacholka from Easter Island. And you can see, just a second here. There we go. And you can see the Milky Way is a bright band of stars there. And actually, I've been there once, and it is really beautiful there. It's a nice dark sky place. You see, the Milky Way is obviously a galaxy with about 100 billion stars. It's got a lot of gas and dust in it. And it's got some interesting things near it. So there are the Magellanic Clouds, which you can only see from the southern hemisphere. They're basically dwarf galaxies, small galaxies that are a few, 5 or 10% the size or mass of the Milky Way. But actually, the reason I put this up here was there's an interesting little object. Oops, let me get this up there. I lost my pointer. I will go back. There's an interesting little object, if you can see my cursor, just below the small Magellanic Cloud there. Okay, that's a globular cluster. Oh, sorry, here's where I would be pointing. Okay, that's a globular cluster. It is a group of stars that are gravitationally bound. They're roughly the age of the universe almost. And they're kind of amazing objects. If you, on this next slide, here's sort of a close-up of this globular cluster, which is called 47 Tucanae. And it's got upwards of 1 million stars in it, in an exceedingly small volume, roughly less than 100 light years. And so if the Earth were on a planet, if the Earth were a planet around one of the stars in this globular cluster, the sky would never get dark. It would be like having 20 full moons all the time. And so astronomy would be almost impossible, at least optical astronomy would. But these are fascinating objects. But the reason I put this up here is because globular clusters were first used to get a much better feel and understanding of what the Milky Way was and where we are in it. So basically 100 years ago, it wasn't clear that the Milky Way was a galaxy. maybe it was the entire universe and everything else was in it. But around 1920, Harlow Shapley at Harvard measured distances or estimated distances to a lot of globular clusters. And he did this by sort of an indirect distance estimator. They're called Cepheid variables. They have a very standard brightness. If you measure the period of the oscillations of the star, you would know its intrinsic brightness. And then from how faint it appears, you could tell how far away it was. And he made this the first plan view map of the Milky Way. So this is like an architect's plan view. The sun is at the center there. And he actually measured the distances to all these globular clusters and put them on the map. And he noticed this obvious thing that we're off to the side of this distribution. And he correctly inferred that the center of this distribution, which was something there, probably was the center of the Milky Way, and that we were not near the center of the Milky Way. That was sort of the first attempt to understand where we are in the Milky Way. He had it roughly right. He had the direction certainly right. The distance scale was off by a factor of a few because the Cepheid star calibrations just weren't that good at that point. So underpinning the calibration of these Cepheid stars that he used for distances had to be a very direct and geometric way to measure distances to stars. And that's what's called trigonometric parallax. And it's just surveying. You measure off a baseline as a surveyor does on Earth, and then you look from two different vantage points and measure the angular shift of some nearby object against the background. And if you measure that angle and you know your baseline, you calculate the distance easily. Well, that wasn't so easy to do. So I'm going to take a little detour and give you the history of measuring parallax or trigonometric parallax distances in astronomy. And I'm actually going to start about 2,000 years ago with this fellow Hipparchus. And he was actually able to measure the distance to the moon 2,000 years ago. And he did it in the following way. He didn't even have to go to a telescope because there weren't any. In Hellespont in modern day Turkey, there was a solar eclipse reported that was a total solar eclipse. And so, let's see if I can get this going. My little animation doesn't want to go. Oh, well, it's slow, but there it is. I've made a little sort of animation of the dark moon here covering the bright sun.
Well, make the speakers louder.
Any problem there? Okay. Whoops. And so this is what happened at Hellespont. The moon went across, it totally covered the sun, and then it went out again. But in Alexandria, in Egypt, the moon made a track as shown on the bottom there. And when it was same time that it covered the sun in Hellespont, it left about 20% of the sun exposed. It went above it. So he probably made a diagram, maybe in the sand, that looked like this. He has the Earth on the left with H for Hellespont and A for Alexandria, and the moon in the middle there and the sun on the right. And if you draw lines through from Hellespont to the upper limb of the moon, it hits the upper limb of the sun, and the same for the bottom ones, and that's a total eclipse. But from Alexandria, as I showed you in that other animation, it misses a little bit, and 20% of the sun is exposed. So with this, you have an angle in here, really tiny angle between the green line from Alexandria and the purple line from Hellespont hitting the bottom of the moon there. And I've drawn it bigger at the bottom here. And he was able to basically, he knew the distance between Alexandria and Hellespont, able to make a small geometric correction to put them above each other, basically. And he knew the angle alpha over here. That's 20% of the size of the sun. The sun is a ½ degree across, so it's 1/10 of 1 degree of angle. And so he could estimate the distance directly from geometry, basically. And it's this projected distance, which was about 700 kilometers, divided by the angle in radians. And there it is down there. And that gives you about 400,000 kilometers. So I think this was kind of a brilliant thing to do in 200 BC.
Mm.
Okay, so. Oh yeah, this is a great illustration of the parallax effect. This is the moon as it would appear from two different places on the Earth, blinked, where they are 7,000 kilometers apart, almost as far apart as you can get. I think it's from Cape Town to Northern Europe. And you can see some background stars on this animation, and you can see how the moon would appear in one place and then the other. It's a huge effect. It's about twice the diameter of the moon. It's about 1 degree on the sky. So that's the parallax of the moon viewed from a baseline of 7,000 kilometers. Well, although this will drive you nuts after a while, I'll turn it off. And so the Earth's baselines that you can get on the Earth just aren't big enough to go much further than the moon and measure it accurately. And so when people tried to measure distances to stars, there was no way to do that from surveying from the surface of the Earth. So scientists at the time, in the Middle Ages and beyond, tried to use the Earth's orbit around the sun as a baseline. And that's diagrammed here on this figure. So here's the sun at the center. Here's the Earth, say in December for some given star. If you know that distance, and you can measure this angle against background stars, you know how far away the star is. And it's pretty simple. To give you an idea of how big these angles are, the nearest star is about 1 parsec, which is about 3 light years. And it would subtend an angle between the sun and the Earth, this angle P here, of 1 second of arc. What happened here? So basically, there were 2 things you could learn from the parallax. One is how far away stars were, which back in the 16, 17, 1800s would be roughly how big the universe is, because no one really knew. There was more to it than the Milky Way galaxy and stars. And the other thing you could prove is that the Earth went around the sun, which wasn't really solidly known in the 1500s, 1600s, and 1700s. If the sun went around the Earth instead, there would be no parallax effect because the Earth would just be stationary. So this started basically the race to measure the cosmos, which is a title of a really excellent book by Alan Hirschfeld. And I strongly recommend it. I'm just going to go through a few of the important characters in this. The first is Robert Hooke. He's a very interesting character in the late 1600s. He was a biologist. He essentially invented the microscope for biology. He was a physicist. He's responsible for Hooke's law for how springs work. He was an astronomer. He was the surveyor of London, and he was the first president of the Royal Society. And he tried to measure parallax of stars, and he correctly understood this effect, which is atmospheric refraction. And so when the sun is rising here in the east, when it's as pictured here, it's actually totally below the horizon. It's just that the light rays from the sun come up and bend through the Earth's atmosphere, and we see it as if the sun were above the horizon. And the amount of atmospheric refraction that happens when looking horizontally through the Earth's atmosphere, is a ½ degree, the size of the sun. So it's a huge effect. And Robert Hooke rightly understood that, that would kill any attempt to measure parallax if you looked at different source elevations, different stellar elevations. So he said, let's look directly vertically up at a star. And when you look up vertically, atmospheric refraction goes to 0. So he built a telescope, apparently in his mother's house in London, that was attached to the chimney and went through the roof.
Wow.
Doesn't sound like a great thing to do in London because it must have leaked, and went all the way down to the basement. And I think he hung a plumb bob to measure vertical, and then saw how much he had to tip the telescope to get a star. The star he looked at was Gamma Draconis. He apparently did this in July of 1669, and then again in October, actually probably in daylight. And he probably measured an offset. We don't really know. There's no record of it. But I would guess he measured about a 10 arc-second offset. He had a lot of technical problems with building motion, telescope alignment, and he was in very poor health, and he gave up this venture. But about 80 years later, this fellow, James Bradley, tried to do the exact same thing with a lot better telescope. So he looked at Gamma Draconis, which went vertically through the sky at transit in London. And he was able to measure, well, he tried to measure the effect. For some reason, when I click to advance, it doesn't want to do it right away. Interesting. Okay. So there it is. The red curve is sort of what he was expecting for a parallax of this star. He didn't know the amplitude of this effect. So this is a plot of declination shift, how high the north-south offset of the star as a function of time over 1 year and the x-axis there. And so he knew it should be at the lowest point in December and at the highest point in June, based on where this star was and where the Earth's orbit is. He didn't know how big that solid red line should be. That's what he wanted to measure. What he measured were these blue points, and these are his actual data. And you can look at that data and you realize it has the exact same form that the red curve does, except it's shifted by 3 months from where it should be. And this totally perplexed Bradley for a long time. He tried a different star and got a similar effect. He rebuilt his telescope and got the same effect and was essentially totally stumped. The story goes, let's see, I think I'm past it now. No, there we go. Story goes, he was on a little sailboat, probably in the River Thames, and he noticed that every time the sailboat tacked, that the telltale, which gives you the direction of the wind on top of the mast, changed directions. So he knew the wind changed apparent direction every time he tacked. And he understood, obviously, it wasn't just a fluke. It was the fact that the motion of the boat affects the direction of the wind. And of course, I think we're all familiar with this. If you get on a bicycle and start going, you'll get wind in your face because you're moving, not necessarily that there's any wind. And so he surmised that, well, if the motion of the boat could affect the apparent direction of the wind, perhaps the motion of the Earth could affect the apparent direction that light comes in from. And so he basically discovered a physical effect called aberration of light. And that's what was responsible for these blue points. And it's a big effect. It's about 20 seconds of arc from peak, plus or minus from peak to peak. When he removed that, oh, there we go. He got an upper limit for the parallax of this star, which was of a half an arc second. That's really a great measurement. So he knew it was more distant than 2 parsecs, or about 6 light years. The true parallax of this star is 2/100ths of a second of arc. So he had no chance of measuring it. That dashed line is the actual effect he would have tried to measure on this star had a good enough telescope to do it. Well, interestingly enough, this confirmed that the Earth moved around the sun probably as well as any parallax measurement would do. So it was actually a very great result. So moving on, we go to William Herschel. And he's a musician and an astronomer, and he made very large reflecting telescopes. And he was basically searching the sky for two stars that were nearby each other. And he wanted to do this in order to measure stellar parallax. This was actually a suggestion by Galileo, that if you want to measure subtle changes in the position of the star, don't just try to measure its total right ascension, its absolute right ascension and declination, or its absolute position. Measure an offset relative to another star that is presumably very distant and so not moving. And so this was why he was making these catalogs of these stars that were nearby each other. And while doing this, he bumped into the planet Uranus and became very famous for that, obviously. About the same period, John Mitchell, a scientist in England, did a statistical analysis of the double stars that William Herschel had cataloged. And he said that by chance, the numbers of stars he was seeing that were so close together was extremely unlikely. And it turns out that, and he pointed out that most of Herschel's double stars were binaries, that are stars that orbit each other. So they're gravitationally bound, they're at the same distance. So that actually proved that not all stars were the same brightness. So that's another really great result. John Mitchell, by the way, also contemplated the idea of black holes, that if you had enough mass, enough gravity, perhaps it could hold light in and not let light out. So amazing stuff for the 1700s. Now we go on to the, I think this is the most interesting part of the parallax story. A fellow named Joseph Fraunhofer. And he was born into a family of 11 children. His father was a glazer, made windows, and they were very poor. None of them had any education. And he was orphaned at age 11. And he was basically apprenticed to a guy who made mirrors, since young Fraunhofer knew something about working with glass. Well, this was in Munich, and in 1801, the mirror maker's building collapsed. It was a 4-story building, killed his wife, and Fraunhofer was down on the first floor with a bunch of shipping pallets stacked up for mirrors, and that held up the debris. And so he wasn't killed. So there was, people around came to see this 4-story building that had collapsed, and they could hear young Fraunhofer crying for help. And there was a big rescue effort, and the local prince, Maximilian Joseph in Munich, came down to oversee this effort. And he also had a businessman friend of his who came along also. And after some time, they were able to pull young Fraunhofer from the rubble, and this changed his life totally. Had this not happened, he probably would have not done anything. We would have never heard of it. Well, the prince took an interest in him. He gave him some books so he could educate himself. Later, he gave him some money so he could buy himself out of the contract he had with the mirror maker. And after that, the businessman friend of the prince, who wanted to develop optics in Germany, in the Munich area, to compete with the British, who at that point in the 1800s made the best optics. And they realized they had known Fraunhofer was a sharp kid, and they thought he might work out well in the company. And basically, after a few years, Fraunhofer was running this company and making excellent lenses. Here's a Fraunhofer telescope that was on eBay a few years ago. I found this picture, and apparently these were exquisite telescopes with gravity drive and just beautifully made. So basically, Fraunhofer became the best telescope maker in the world, and he's known for discovering what are called Fraunhofer lines, or absorption lines, in the spectrum of the sun. So he's basically the father of stellar spectroscopy. Well, his last telescope was commissioned by this fellow, Friedrich Wilhelm Bessel. And Bessel wanted to measure stellar parallax. And so he asked Fraunhofer to build him a telescope where he took after making this beautiful primary lens, this is a refractor telescope, so you look directly through it. Take the primary lens, which is, must take a year or two to make, and cut it in half. And then put it and mount the two halves next to each other so that you could slide them with respect to each other a little bit. And that way you could superpose two stars from different positions on top of each other, because you get two images from the two halves of the lenses. And that sort of got around the turbulence in the Earth's atmosphere, the twinkling of stars, because if the stars are close enough together, they sort of move together. And so he was able to make really accurate measurements, and he made the first credible stellar parallax measurement in 1838. He looked at a star called 61 Cygni. He picked out this star actually because it was known to be one of the fastest moving stars that move across the sky. And he figured if it's moving fast across the sky, it must be nearby. Here's his data, which you can get, and I digitized it and then I fit it to see if I could get the same results he got. He got a parallax of 0.314 arc seconds. He had two background stars he compared it against, and the red data points up there are from one star and the blue for another, and the solid lines are parallax fits, what you'd expect depending how far away it is. And you can see you get a parallax of 0.37 arc seconds from the red star and 0.25 arc seconds parallax from the blue star. If you average those two together, you get about what he quoted. So he made really excellent measurements. Turns out the true answer, the modern day accurately measured distance parallax of the star is 0.287. And so you can see he was within 10% or so of the true answer. So let's go back to our picture of the Milky Way. That's sort of the history of stellar parallax. And in the next, 150 years after Bessel, there were a lot of parallax measurements made, especially once photographic plates were used in astronomy, which made this a lot easier. But it's very hard optically to measure distances to very distant stars. First of all, parallaxes get very small. And secondly, there's a lot of dust in the Milky Way, and it absorbs optical light. So you really can't see very far optically into the Milky Way. So that band of stars you see for the Milky Way, those are all pretty close stars. They're in the general solar neighborhood. There is a great astronomy mission the Europeans have up right now called Gaia, which measures stellar parallaxes with accuracies approaching 10 micro arc seconds, 10 1/millionth of a second of arc, which is really a small angle. However, even that great telescope in space can't see through the dust into the Milky Way. So they can only really map areas near the sun. Okay, so what does the Milky Way look like? That's what I've been working on for a long time. And basically, most astronomers feel it probably looks like a mashup between these two other galaxies. The galaxy on the left has two nice spiral arms and this bar going across it from about 9 o'clock to 3 o'clock here on this image. So this is a barred spiral galaxy. Here's another galaxy that doesn't have a bar, but it's got more spiral arms, roughly about 4 spiral arms. And we think the Milky Way probably has about 4 spiral arms. In fact, pretty sure now. So if you mix these two galaxies up in some way, you might get something that looks like the Milky Way. The other way to figure this out would be to, if this were the Milky Way and we put the sun where I just put the dot, that circle is about as far as the Gaia satellite can easily see because of dust in the Milky Way. Okay, the other way to do it, which would be great if we could do it, is build a spacecraft with a camera let it travel above the Milky Way and take a picture. And let's say the sun on this artist's conception, I think, is supposed to be right here. Of course, it would take millions of years for the spacecraft to get to this height above the Milky Way. And then it would take about 10,000 more years to transmit the picture back. So although it'd be great if we could do this, we can't. So how to do this? Okay, so this is my most likely twin of the Milky Way. It's a galaxy with a name UGC 12158. It was actually photographed by the Hubble Space Telescope. And the only reason they photographed it was there was a supernova in it. And that's why they took a picture, took some data. So if this were the Milky Way and the sun were where I put this yellow dot near the top, if let's say we wanted to measure a newly born star in this spiral arm here, we'd like to know its distance. So we do a trigonometric parallax measurement. I'll show you in a minute how we do it. And then we could measure that one and go on like that. And we could basically, by doing that, trace where this spiral arm is and map it. So how do we do this? You're not going to do it optically, as I said, because you can't see through the dust in the Milky Way to do it. But radio waves will go right through all the dust in the Milky Way, so we can see right through the Milky Way. And with radio telescopes, you can do a neat trick. You can put telescopes all over the Earth, record the data on computer disks, and bring it back to a central computer and process it so you can get an image that your eye could see if your eyes could see radio waves, and you'd have the same resolution as if your eye were as big as the Earth. So you get astounding angular resolution by this technique. It's called very long baseline interferometry. And these are the telescopes I use. I wish they were really that big in life, but they aren't. But they're spread from the Virgin Islands to Hawaii to New England. And it's really a fantastic system. So what angular resolution can we deal with here? Can we get? The human eye can resolve about 40 arc seconds. What is 40 arc seconds? I'm trying to remember what I used to use for an example. Well, the one I know is if you play golf and you're on a par 3, the flagstick, the pin itself, is about 40 arc seconds across. And so that's a pretty small angle. The human eye can barely resolve that. The Hubble Space Telescope can resolve much finer angles. They can get about 5/100ths of an arc second. But with this array of telescopes that spans the Earth's diameter almost, you can get down to about 500 milliarc seconds, and sorry, micro arc seconds, 0.0005 arc seconds. And with that resolution, if you put a car on the moon, you could resolve its headlights. You could tell that there were 2 headlights and not 1 if it were bright enough. So it's really an astounding angular resolution you can get with the VLB array. And you can do even better than that if you want to measure the centroid position of a star. And with that, we can measure positions relative to a background source with an accuracy of 10/1,000,000ths of an arc second. And with that accuracy, we can get a 10% accurate distance to a star that's past the center of the Milky Way. Okay, so we've been doing this for about 10 years now, trying to measure the distances to very young stars across the Milky Way. And this is the results to date. And this actually combines our data with the very long baseline array and data from a project in Japan that has 4 radio telescopes that's doing the same thing. So this is a plan view map of the Milky Way. The 0, 0 position where there's this red star here is the center of the Milky Way. The sun is up here at y-axis about 8,000 parsecs. And each dot on here is actually a very massive young star that was just born that we've measured a parallax distance to. These are all color-coded by the spiral arms that we think they are in. And it's been, it's actually changed our picture of the Milky Way quite a bit. Let me just run you through a few examples of it. Let's start here. The red ones, that's the outer spiral arm of the Milky Way. That's its name, the outer arm. And we're starting to trace that pretty well. We would like more points down here, and we're working on that. If you come closer to the sun, the black points are what are called the Perseus Spiral Arm. And that was thought to be one of the two dominant spiral arms in the Milky Way. And indeed, we find lots and lots of massive young stars up in this area here that I'm circling. But we were quite surprised that there aren't very many down here. There's some, but not very many. It turns out a lot of them that we expected to be there ended up in these cyan points closer to the sun than the arm, the Perseus arm. The cyan points are what are called the local arm or local spiral arm in the Milky Way. And it was thought to be a very, very minor structure in the Milky Way. But it's really has a lot more star formation comparable to that in the Perseus arm. And so it seems to be an orphan little, not so little, arm segment. It's a piece of an arm that just, the sun just happens to be near. If you go inward from the local arm and the sun, you get the magenta points. That's the Sagittarius Carina arm. And then even closer in the blue points are the Crux Scutum arm. Whoops. And then it gets really complicated in the center of the Milky Way. That ellipse is supposed to represent the bar in the center of the Milky Way, which we know is there. And we're actually trying to get more points in the bar, but it's not an easy job. So one thing we've learned is that the Milky Way is basically a four-armed spiral. And that actually has been controversial in the last 10 or 20 years. Because if you look at stars, it looks more like a two-armed spiral. But if you look at young massive stars, blue stars, which you can't really see optically because of the dust problem, it's clearly a four-armed spiral. So we've learned that. So the other thing we can do is we can try to fit a model of spiral arms to the data, and we can do that pretty well, at least in this portion of the Milky Way, the upper right corner here, and then we extrapolate that where we don't have much data. Okay, so what we do know now is that at any point from this model, at any point along a spiral arm, we know how far it is from the sun, and we know how things move, how stars move, at what speed in those arms. And so we can actually do an interesting little trick with this. Oh, I was going to point out, yes, we now also learned that we are 27,000 light years from the center of the Milky Way. And we move at about 240 kilometers every second in a nearly circular orbit around the galaxy. And in fact, the last time the sun was in this part of the galaxy, dinosaurs were roaming the Earth about 200 million years ago. It takes 200 million years for the sun to go around the Milky Way. Okay, so let's go back to that picture of what I think a Milky Way lookalike might be. And I mentioned we make this map by measuring distances by parallax to these massive young stars. Let me clean this picture up a bit and draw a different line. So let's say we're looking out through the Milky Way along this line. If there were an object, a star, a young massive star there, and if it's in a circular orbit about the center of the Milky Way, as most young things are, it would be moving in this direction given by the white arrow. And we would measure a Doppler shift or a velocity that's pretty big because it's moving directly away from us. If we had a star in this next spiral arm of the Milky Way, you can see it would be moving if it's going in a circle at a different orientation, and that would change the velocity we would measure. And if it were in the outer arm there, if it ever comes on here, there it is, it would be moving in yet a different direction. So by knowing where the spiral arms are and how things move in them, we could take a measurement of an object whose distance we don't know, try to match it to one of the spiral arms. And if it matches well, we can be pretty confident that it's at the distance of that spiral arm. Now, this allows us to take catalogs of thousands of stars that have just formed, of star forming regions, where people have measured the coordinates, where it is in the sky, and the Doppler shift velocity, how it appears to be moving away from us or towards us. And do this matching to spiral arms, and we can come up with a much more complete image of what the Milky Way would look like. And this is, I think, the best visualization of the Milky Way that is based on solid data. And so that's you can see the spiral pattern in the dark blue points. There are some points in cyan there that when you try to do this matching, that doesn't work. And so those we don't know very well. But this is a pretty complete view of the Milky Way. And so what I've done is I've given this to some digital artists. Actually, some of my Chinese colleagues at Nanjing University have some digital artists. We give them this and say, how would it look if it were to look like other galaxies, but with this pattern? And this is what they've come up with. And so that's, I think, the best artist's conception of the Milky Way to date. It's based on solid measurements of distances to lots of stars, and then this technique of, again, getting thousands of distances by leveraging the model of the spiral structure. So that's where we stand today. The model is less certain in the bottom left because that area of the sky can only be done from the southern hemisphere. And so I've been actually going down to Tasmania until COVID. Tasmania is a state in Australia, and trying to get an array of telescopes like that very long baseline array put together. And we've got now 5 telescopes, 4 in Australia and 1 in New Zealand, that are actively doing this. And we're in the middle of measuring a lot of objects down there to try to confirm, the left side of this picture to make it more reliable. So until COVID, I haven't been down there now in a year and a half, but I look forward to going back and completing this map. So thanks for your time. And if you have any questions, I'd be happy to answer them.
I have a quick one. Actually, 2. The first one is the easier of the 2, I think. The UGC galaxy that you used as an initial model. There's a huge circular object at 11 o'clock. Has anybody looked at that cross-eyed other than me?
This sort of S-shaped thing up here?
Yeah, it's almost like a circle. Yeah.
Yeah, it's got I've noticed that too. I have no idea what that is.
Okay. And
It's
in the
obviously-
Chinese model, there's it looks like it has Hoag's object at the center. It doesn't look like part of a spiral arm.
Sorry, which thing now?
The last galaxy you showed, the Chinese elaboration on your data.
The artist's conception here. Yeah.
Yeah.
So if this is the galactic bar, what's the question?
The ring around it looks like Hoag's object, and I was wondering what the dynamics are that would produce that. I'm also curious about what the dynamics are that produce the bar. So if you could tell me that, I would be satisfied.
Okay, 2 questions. Let me first go. This almost circular structure here It's called the 3 kiloparsec arm in the Milky Way. And it's thought to be nearly circular. They made it quite circular. We don't know in detail the exact shape of this because we would have to measure positions to a dozen objects in here. And we only have a few objects in there right now. And they're pretty far away so that they're not that accurate. Okay, but that is a structure that's known in the Milky Way.
Cool.
Okay, so the bar, why are there bars in spiral galaxies? The simplest explanation is that if you take a disk of gas and put enough mass into it, it becomes unstable. And in numerical simulations of rotating disks of gas, they are unstable often to forming a bar in the center, at least for some time. So it's a hydrodynamic instability.
Would that be part of the same shock wave or whatever that's responsible for the arms?
Bars can easily form arms. In fact, if I went back to the, let me see if it'll be a long way back. When I took those 2 galaxies that I said, let me go back to them. It's worth it. Goes back fast. There, here we go. So the galaxy on the left, it's got the strong bar, big, huge bar. And you can see these spiral arms form at the ends of the bar.
Yeah.
They start there. So yes, if you put basically something that spins, a lozenge, an elongated object, and spin it in a fluid, it will form spiral structures outside of it. It'll make waves. How spiral arms form in a galaxy like this, it's not as clear. Basically, the numerical simulations are getting really good at this. People can now do 3-dimensional hydrodynamic models of huge numbers of stars, I'll call them, where they now can do something like almost one object in their simulation per star in the Milky Way. So that's 10 billion objects, 10 billion points in their calculations. So these are huge calculations they do, and they spin things around, and they find that if there are clumps of things in there that seed spiral arm formation, like molecular clouds, something that's massive in the galaxy, you tend to form arm segments. And you can see that actually in these things. You can see, this sort of quasi straight line thing here. And then you can almost say you can make this spiral up out of segments. And that's what they see in the simulations. And so apparently these segments, they shear as the galaxy spins. There's some non-linearities in the effects. And then they tend to they link up for a while. And then they probably disperse and new ones would form. So that's, I think, the best explanation for how spiral structure exists in galaxies.
I think there's also an effect from how the stars flow through the galaxy, because you can have very simple circular flow of stars and gas, and sometimes you have what's called a hot disk, where there's a lot of random motions, which I think also affect the spiral structure, and it can look a little bit more random.
Yeah, that's right. And if a dwarf galaxy falls through the Milky Way or some galaxy, that can also trigger disturbances that might end up with spiral structure. It's basically an open field right now. It's not totally well known.
Mm-hmm.
I think the simulations that are now being done are probably the key to it. It was too tough a problem really to do with pencil and paper.
So Mark, how does your mapping compare with the mapping that uses pulsars and what is known as their dispersion measures? Because they also produce a 4-arm spiral pattern, and that is based on the gas. which affects this dispersion measure of pulsars. It's basically the timing of the pulsars as they're received. Is the comparison reasonable?
Somewhat. I mean, you have to know the distances to the pulsars to do that. And that's not so easy to do. And so a lot of assumptions go in. And I think the pulsar map, which is basically the Taylor-Cortis model, Cortis-Taylor model. I think it's, largely based on earlier models, based on young star distances that were pretty sparse and not terribly accurate by Georgelin and Georgelin. So the pictures have been evolving, and well, the old models did have roughly 4 spiral arms. That was sort of the best guess. And then the infrared space telescopes tried to look down tangencies of spiral arms in the Milky Way and said, well, we only see excess of stars on these tangencies in 2 arms. So we think stars are only dominant in 2 spiral arms. And we don't have a real good answer for that yet, because what we're looking at with radio waves are quite different than old stars. So there's a lot of open questions, but I feel totally safe in saying we live in a 4-arm spiral galaxy. There are extra little things floating around, but that's the dominant structure.
What wavelength were you observing? Like 2 centimeters or 3 centimeters?
Okay, so yeah, I didn't really go into what we're using. We use what are called masers, okay, which are molecular gas that's right around these newly formed very massive stars, and they have trace constituents of water and methyl alcohol and many other molecules, but those two provide very strong natural maser emission. And maser emission, for those of you who aren't in the know here, are very much like lasers, except at radio frequencies. So if you have a laser pointer, you get a really bright spot of light out of the laser pointer. Well, we look at really bright spots of light, of radio light, from the maser emission in clouds of gas that are around these very young stars. And so those are our targets. So the frequencies or wavelengths, we use about 1 centimeter for water, 22 gigahertz. And then methyl alcohol is a great one also. And it has transitions at 6.7 and 12 gigahertz that we use. So about 4 centimeters and 3, 2.5.
So I was interested in your data where you showed the little dots of different colors. Maybe you can go to that slide right now.
Yeah.
Because
That's an interesting detail. It's important, actually. There.
Yeah. Okay. And that figure there, you see that the dots are following the spiral, what you would call spiral arms, but there are also white dots which don't seem to follow spiral arms. And
exactly.
And I'm thinking that, I mean, your survey is not unbiased. You are looking for specific points in the sky. So maybe you're missing a lot of places between the arms. So are you sure you're getting the arms and not something between the arms?
There probably are some things between the arms. And, this little white group here seems to be between the Sagittarius and local arm. This clump in here, we think it might be sort of a spur-like thing, the Aquila spur. I didn't mention the color coding here is not based on this map for the most part. It's based on what we call longitude velocity plots of carbon monoxide emission in the Milky Way. And you can see spiral arms in those plots. They're curlicues in this position velocity plot, but you don't know distance from that. So you can, from the position and velocity, you can say, well, this is obviously in the Perseus arm. And so that's why we color it black. But you wouldn't know where it was in distance. So for example, this black dot out here, we're pretty sure it's in the Perseus arm. This is one of our least accurate measurements. The bigger the circle, the more accurate the measurement is. So we try to emphasize that. So this black dot is really probably someplace in here. And that's just measurement error. That's probably about 15% measurement error. So that's why the color coded, if we didn't have the color coding, if you just made all these dots the same color, you could trace the outer arm and the Perseus arm and maybe some other little segments like the local arm, but you'd start to get totally confused in here. You'd say, I don't know what those are, So it's really important that we're able to color code them by arm without the knowledge of the distance.
Well, it'll be interesting when you fill in those spaces with more dots.
Yeah, here's where we want to really go for. The ones down here are going to be very hard. It's so far away. We do have one point here I should have mentioned down at the bottom. We got lucky. There's no way to know when you look at the Doppler shift of anything in that direction. It's always near zero.
Is that your error bar? It looks pretty big.
Yeah, but that's 20 kiloparsecs away. That's a 10% error bar.
Yeah.
That's about as good as you can do. The angle, the parallax angle for this one is 50 micro arc seconds, plus or minus 6 is the measurement. So micro arc seconds.
No, it's still pretty impressive that you can get something on that side of the galaxy.
Yeah.
Yeah,
We'd love to get more.
Indeed.
this is some of the most precise work going on in astronomy right now. And I know it's been a hard fought battle. And I thank Mark for sharing this research with us. I also was very pleased that you featured the book Parallax, The Race to Measure the Cosmos by Alan Hirschfeld, which is truly a great book on how we figured out how far the nearest star was, and in so doing, determined that we were going around the sun and not vice versa. It's a great book full of characters, that's for sure. So unless we have any other questions, Michael.
This is not a difficult scientific question. It's the sort of thing I'm going to get asked someday, and I don't know the answer. The disk is spinning, and we're moving through it. Are we going spinward or anti-spinward?
Oh, we're going in the direction of rotation.
Oh.
On this plan view of the Milky Way, the galaxy rotates clockwise. And almost everything, especially anything massive or young, is moving clockwise, and mostly in nearly circular orbits. The sun's eccentricity in the orbit is about 10%. So its non-circular component is about 20 kilometers per second, and circular component is near 240.
So our velocity through the disk is added to the velocity of the disk.
Well, the disk. Almost everything is moving together.
Okay. So we're not moving through the galaxy.
Well,
that's what I thought we were doing.
Okay, the galaxy and the gas, gas and dust and stars, which makes up most of it here, is all going to first order, to use that terminology, in circular motion at 240 kilometers per second. Right. Until you get close to the center.
We're like in this carousel, right? We're all the horses are like all the stars, and we're all moving together around the center.
Right, right. Now there's some small non-circular components, and those do interesting things, but the simplest model is we're just all going in a circle.
Okay, thank you.
Yeah, and to you. Oh, it's for me. Okay. Just it's a little bit on the side, but you said that we can process radio wave observations from different points on the Earth and combine these observations to increase the resolution. And I wonder why we cannot do the same with visual observation.
That's a good question. The answer is basically that it's very hard to make an optical amplifier.
Mhm.
Can't really do it. There are quantum mechanical effects that really make it almost impossible. So, but at radio wavelengths, you can make amplifiers. We've all used them in radios and every place else. That allows us to make an exact copy of the signal as strong as we need it. And then when we mix it or multiply together a signal from one telescope with another, we don't lose anything. We can do it with every telescope. Where if you do this optically, and people do optical interferometry, you have to divide up the light. And so if you have 10 telescopes and you're going to make an interferometer, you've got to divide up the light from any one telescope in 9 parts going to all the other telescopes. And so you get 1/9 the light. And also you have to do that at the same site. It's pretty hard to pipe light around the Earth too far. It can be done with fiber optics, but there are real problems with stability in terms of path lengths, which gets complicated here. So the short answer is at radio wavelengths, we can amplify our signals, we can make copies of them, and that allows us to do this trick. I didn't mention we have to, of course, align in time all the telescopes perfectly, nearly perfectly. So we have to use atomic clocks at each telescope so that we can align them later. And we use what are called hydrogen maser frequency standards, which are good to, better than a second in a million years.
Wow.
Okay.
That's good.
That's how pure the oscillation is for those clocks.
Beats my Timex.
Of course, there are other problems as well. Is there the interference from the atmosphere? The atmosphere doesn't interfere with radio waves as much as with light waves. And with light waves, you're going to have, because of the turbulence, there's a phenomenon known as seeing. The turbulence of the atmosphere will mess up the path lengths of the photons coming through. So it's hard to combine the signals coherently.
However, it turns out that fluctuations in the water vapor in the Earth's atmosphere above our radio telescopes is the largest source of trouble for us.
Mhm.
Limits us. We go to great lengths to calibrate stuff like that, and we can calibrate almost everything in the VLB array to an accuracy of about 1 centimeter in location and 1 centimeter in optical path. And a centimeter in optical path is 1/30th of a nanosecond of time. It takes light 1/30th of a nanosecond to go a centimeter. So we have to get everything right to that level of accuracy to make measurements this accurate.
Yeah.
It's even worse at optical wavelengths. It's even
Yes,
worse.
yes.
Thank you. Mhm.
And so, for example, we have to worry about solid Earth tides. So as we sit here on the Earth, it's being stretched by the moon and by the sun as we go around. And it moves up, and we move up and down by about 20 centimeters every day.
Wow.
We don't notice it, but we have to take that sort of stuff into account in order to make measurements as precise.
Thank you.
Yeah, it's quite an accomplishment. So already, congratulations. Okay, well, this has been great. I feel like I know where I am more. If only I knew where I was in Rockport a little better. And I thank you all for coming, and thank Mark especially for a scintillating talk.
Yes, thank you.
Thank you.
Hi, guys.
Bye-bye.
Bye.
Bye.